as we talked about before, you can never know the exact location of an electron at any given moment. You can only talk about it where it is in terms of it most likely is in this region. This is Heisenberg's uncertainty principle. We can never know for certain where an electron is at any given moment and how fast it's traveling. The more you know about one, the less you'll know about the other. But we do know that two objects cannot exist in the same location at the same time. So each electron has a particular address or area that we assign it to when we're talking about where it is. This is called the electron's quantum numbers. And it's a 4-number address for where the electron is. And it might look something like this. And each number corresponds to a particular thing, a particular part of the address, the 3-dimensional address of where that electron is. The first number is called the quantum number, and it corresponds to how far the electron is from the nucleus. The second number corresponds to the shape of the probability distribution. The third is which area of that shape it is. And lastly is the spin, in which direction it's traveling. And we get a general idea of how to do that. When you take AP Chemistry, I will teach you how to write the 4-number address, the 4 quantum numbers for an electron. But before you do that, we got to learn some basic principles of quantum numbers. We need to learn how to write the electron configuration, which tells us where an electron is, how far it is from the nucleus, what shape it is in, what shape its probability distribution is, and gives us a general idea of the energy of that electron. So before you start writing electron configurations, you should number your periodic table. Go down the columns, because these correspond to how far an electron is from the nucleus. These are called your quantum numbers. They're the distance, or they're related to the distance the electron is from the nucleus. The greater the quantum number, the further the electron is from the nucleus, the more energy that electron has. The next thing you need to know is that the periodic table is broken into blocks that correspond to probability distributions. The first 2 columns are called the S block and correspond to an S shape. S's are spherical, meaning the probability distribution of where an electron can possibly be is spherical or round. And it's one of the largest shapes. Groups 13 to 18 are the P block. And P blocks look like dumbbells. So you can have a P that goes up and down. You can have one that goes left and right. And you can have one that comes into and goes out of your screen. So you can have up to 3 different P's. You can have one on the y-axis, on the x-axis, and on the z-axis. So for a total of 6. 1, 2, 3, 4, 5, 6. Isn't it funny how that worked out? S's can only have electrons up or electrons down, to the left or to the right. So S's can only hold 2. 1, 2. Isn't it funny how that worked out? The dip in the center is the D block. So, but unlike S's and P's, S's, wrong color. S's are really big spheres. P's are really big dumbbells. D's are itty-bitty little clover leaves that can hold up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they're closer to the nucleus. They're tightly woven little packs of energy of electrons. Their shapes are awkward and funny, and I'm not going to be able to draw them to any real interesting ways. If you're really interested in what the shape of a D sublevel or D orbital looks like, feel free to Google it. Lastly, at the very bottom of your periodic table, the lanthanides and actinide series, they constitute the F block. And Fs are even smaller than Ds. And their shape is so upside down, crazy, and backwards that I'm not even sure you're going to be able to Google it. But they can hold up to 14 electrons for each F block. The last thing we need to talk about before we start doing some electron configuration is you need to realize that helium's a bit of a freak in this case and should be cut off and moved over here next to hydrogen, because helium only has 2 electrons, and it's not as though those electrons can fit into a p orbital because you have an s that's not completely full. S's, once they're full, you can move down to the next block. Once your orbitals are full, you can move over to the next orbital or the next quantum number, which means anytime we get to a noble gas, we're going to either move down the periodic table or, well, not or, we will move down the periodic table to the next quantum number, to the next period. That being said, let's start writing some pretty simple electron configurations. So let's say test A rolls around and your test says, give the electron configuration of sulfur. It's kind of like playing Battleship. You have to say where these electrons are and where you're going to move down. Each time you move over or through a sublevel, you have to specify what elements or how many electrons you passed. Remember, we moved helium. All right, so you always start at the top. Start at the top left, just like reading. And we're just going to talk about how many electrons we are covering each time. So I'm starting up here. If I go start here, I'm at 1s. This would be 1s1. But I don't really care about that until I close out a block. So I'm going to move over until I close out the block. All right, this block's now closed. So that's 1s, and I moved over 2 electrons, so I'll put 1s2. That closes out all of these. All right? When I get to the noble gases, I can move down. Now I'm in 2s, and I'm going to move over until I close out a sublevel. I'm going to close out the s sublevel. So this would be 2s2. And I keep moving over, not hitting anything, not hitting anything, blah, 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 blah. All right, I've got somewhere. Where am I at now? Well, I'm still in 2. This is now the P block. And I'm going to go until I close out the block or I get to the element I'm looking for. Close out the block, that moves me over 6 spaces. So 2p6. When I get to a noble gas, I can move down. So now I'm down here. This is 3s. Move until you close out a sublevel. So I'm going to close out the s sublevel. I moved over 2, so that's 2s2. Not hitting anything, not hitting anything, blah, 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 blah. All right, I'm over here now. This is the third principal energy level. We're in the P block, P sublevel. Moving over 1, 2, 3, 4 gets me to sulfur, so 3p4. So we could say sulfur's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Or we could condense that and say the valence electron, the very last electrons in sulfur, the very last electrons in sulfur have an electron configuration of 3p4. And it'd be like kind of playing Battleship. Where's 3p? Well, here's 3. Here's p. 3p4 is sulfur. There's another shortcut we can talk about, and it has to do with the noble gases. You move down each time you reach a noble gas. So they're kind of a shortcut or a waypoint. We know exactly where they are. For example, this 1s2 constitutes helium. So I could say, okay, start at helium and then go forward. 2s2, 2p6, 3s2, 3p4. But that's not the nearest noble gas. What's the nearest noble gas? It's kind of like if you were telling someone to get to your house, you would say, okay, take 64 to Jefferson Boulevard. If anyone has ever been to Newport News, they know where Jefferson Boulevard is. It's like the biggest road in the area. All right? It's a waypoint. You know how Google starts your directions at how to get out of your neighborhood? Well, you kind of know how to get out of your neighborhood. When it comes to the periodic table, electron configuration, you kind of know how to start at a different, at a noble gas. So we could start at the nearest noble gas without going over, because you can't go backwards. So we're going to start here. This noble gas, which I just scribbled out and can't read now, is neon. So we're going to start at neon. And by saying neon, that constitutes all of this. And then we just need to talk about, okay, how far past neon do I need to go? How far off of Jefferson do I need to go? Well, you need to go 3s2, crosses through these, and then 3p4 takes you to sulfur. This is called noble gas notation. Now be careful. If I ask you for the electron configuration, I am asking for this whole thing, and you will lose points. But if I say, give me the electron configuration, you can use noble gas notation, then please, by all means, take a shortcut. Tell me the swift directions. All right, let's do the electron configuration of titanium. I am titanium. You can pardon my singing voice if you'd like. To make sure you've got it, I am not going to do the noble gas notation. I'm going to go through the entire electron configuration. But there's a trick here. Titanium's in the D block, so we're going to have something that's a little different to start with, or to end with. So once again, you start with hydrogen, and remember that helium is right here. So I start with hydrogen. I'm in 1s. 1s2 takes me to helium, and I can move that in. Hold on, I need to make this a little smaller, because we're going to have a lot of electrons here. I got 22 electrons. I need to tell you where they are. Now, once I reach a noble gas, I can move down. So now I'm in 2s, and I'm going to move over 2 spaces to close those out. Moving over, I'm over here now. This is 2p. Close out 6 spaces. I'm over here. This is 3s. Move over 2 spaces. 3s2. 3p. 6 spaces. 4s. Move over 2 spaces. Now we're hitting the D's, and you might go, oh, well that would be 4d2. And you would get a big old X. Wrong. Why is that wrong? Well, think back to when I was talking about their shapes. Rewind me if you have to. Sphere, or S, are spheres. P's are dumbbells. And I said D's are weird-looking little shapes. But I specifically said they're smaller. They're closer to the nucleus. So when you get to the D sublevel, when you get to the D orbitals, they actually bump up 1 quantum energy level, 1 quantum number. Because these numbers on the outside here correspond to how far an electron is from the nucleus. So if these D orbitals are closer to the nucleus, that means they're going to be 1 quantum number greater, or 1 quantum number less, if you want to think about them in terms of 1, 2, 3, and 4. They're closer to the nucleus. They have less energy. So D's will start at 4, and then move, or sorry, at 3, and then move down. So the highest D orbital on the periodic table at the moment is 6d. So titanium would be 3D2. Because it bumps up one energy level. It's closer to the nucleus. If you were going to do the electron configuration of europium, and this time I am going to skip to the noble gas notation, europium is in the F block, which is cut out of the periodic table here and here. The lanthanide series cuts out at La at 57. The actinide series cuts out at 89, actinide. So the nearest noble gas, following backwards, is xenon. So I'm going to start at xenon, and I'm going to go forward. All right, from xenon, that closes out everything before xenon, and closes out all of this, and all of this through here. Okay, so I'm going to move forward from xenon. I'm going to go 6s2. And when I get to that 6s2, well, now I'm going to be starting to hit the D block. But before I can start into the D block, I have to go through the Fs. So I'm going to go, D block would be 5D. That means this is even closer because the Fs are even smaller than the Ds. So this is actually 4D. Now I just got to count over. 4D1, 4D2, 4D3, 4, 5, 4D6. That would be the electron configuration of europium. Now the last thing to talk about with electron configuration is ions. Remember that noble gases are stable. They have the perfect configuration of electrons. Their electrons are quote-unquote happy because there's an equal pull from the nucleus as there is there's enough pull from the nucleus to keep those electrons in a pretty stable probability field around the nucleus. They're in pretty stable orbits. I use the term orbit loosely because it's not as though they're orbiting like planets. Elements will gain or lose electrons to become more stable. Things want to be stable. They want to be at their lowest energy levels possible. And stability is that lowest energy level. So look at chlorine. Chlorine is very close to being the same as argon. The only thing throwing it off is this 5. It is short 1 electron. So chlorine can add 1 electron. If chlorine adds 1 electron to its outermost orbital, and by adding an electron becomes negative, what we call an anion. If it adds that 1 electron to that 3p orbital, it can become stable. It's much, 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 much more stable than an element, than an atom of neutral chlorine. On the flip side, we have potassium. Potassium is really close to being like argon, except for it has an extra electron. So what it can do is it can give up its electron or lose it. If it gives up its electron, it's going to get a positive charge and become what we call a cation. Cat has a T in it. T's are positive. Cations are positive. Anions are negative. When it loses that last electron from its outermost orbital, it's not as though that orbital necessarily goes away. It's still make-believe there. It's just nothing's in it. Your next lab, or the lab you'll do next, we will talk about how you can excite electrons so that they jump up an energy level. And when they come back down, they release light. And different metals will release a different color light. And that'll be your flame test lab. Sorry this video is so long, but I hope it was worth it for you.